We now move to our second main guest lecturer, Dr. Mila Hojilla-Evangelista. Dr. Hojilla-Evangelista has been a research chemist for more than 20 years at the USDA ARS National Center for Agricultural Utilization Research in Peoria, Illinois. She received her BS in Food Technology and MS in Food Science from the University of the Philippines, Los Baños, and PhD in Food Technology from Iowa State University. She has authored more than 130 publications and presentations on value-added products, particularly proteins from processing of soybeans, corn, and alternative oilseed crops. She is a fellow of the American Oil Chemists Society and the American Institute of Chemists. Dr. Hojilla-Evangelista is a recipient of the 2018 Iowa State University Food Science and Human Nutrition Alumni Impact Award and the 2018 Distinguished Alumni Award of the College of Agriculture and Food Science at the University of the Philippines, Los Baños. Dr. Hojilla-Evangelista.
Okay, I'm just getting my screen set up. Thank you, Dr. Nina Cadiz. I am honored to be here. Let me start with a brief overview of my agency. The Agricultural Research Service is the chief scientific in-house research arm of the USDA. It runs 700 research projects under 50 national programs with an annual budget of $1.2 billion. We have 8,000 staff stationed in more than 90 locations across the United States, of which 4 are regional research centers. Eastern Lab is in Widmore, Pennsylvania, Southern Lab in New Orleans, Louisiana, Western Lab in Albany, California, and the Northern Lab, now known as the National Center for Agricultural Utilization Research, is in Peoria, Illinois. NCAR is the largest of the regional research centers with 250 scientists and support staff working in 7 research units. My group is Plant Polymer. Did you know that NCAR scientists developed the process to mass produce the antibiotic penicillin? For this impactful work, our center was named an International Historic Chemical Landmark. Our other discoveries have been transferred to many consumer products. The Plant Polymer Research Group does basic and applied research on modifying natural polymers and develops new bio-based products from agricultural commodities, like the Super Slurper modified cornstarch, which can absorb water in hundreds of times its weight. This starch is used in disposable diapers and in fresh meat packaging as liners. We currently have 3 umbrella projects, and the work I'll present today is part of improved utilization of proteinaceous co-products from crops. There has always been interest in plant-based proteins, but the demand for them seemingly exploded this past 5 years. The demand is driven by a projected substantial growth in world population in 30 years and the consequent rise in protein consumption. Currently, soy and corn proteins dominate the US food and feed markets. But new plant-based sources have entered many sectors of the market with notable sales and growth. Still, more plant proteins are being sought. At our center, we have done the first studies on proteins in some alternative oilseed crops. Coriander is known to most people. It is cultivated as a summer or winter annual and is best known as a spice crop. The young plant is sold as the fresh herb cilantro, while the seeds from the mature plant are dried and sold as dried seeds, ground spice, or extracted for its essential oil, which is used as a flavor agent or in personal care products. To tap the other components of coriander seed, we developed an integrated oil process that produced essential oil plus the triglycerides and a protein-enriched meal for further extraction. Cuphea seed has 25% protein and 32% oil that is rich in medium-chain fatty acids and triglycerides. Cuphea can be a domestic source of these fatty acids for use in detergents, cosmetics, and lubricants. Camelina is a plant in the mustard family. It grows in marginal lands and planted in rotation with wheat. Its seed has 30% protein and 40% oil, which is mainly unsaturated fatty acids that may have nutraceutical value. Pennycress is historically a weed. It is a winter crop that is planted in rotation with soybeans, which negates the food versus fuel issue. The seed has 25%, 21% rather, crude protein and around 30% oil, which is rich in erucic acid that is used in industrial lubricants. For these four oil crops, the press cake is the protein co-product of oil process, and finding use for them will increase the value of the crops. Our research goals were to determine the chemical and functional properties of proteins in coriander, Cuphea, Camelina, and Pennycress, and identify the possible uses of these protein products. Our work determined the composition and soluble protein classes and the effects of oil pressing on protein properties. We performed bench scale extractions of the protein and tested the functional properties to identify possible uses. For pennycress, we scaled up the protein isolate production and tested the protein in films and fibers. The four oil seeds contained substantial oil ranging from 18 to 35%. Protein contents ranged from 13 to 27%, with coriander having the least amounts of both oil and protein, but the most amounts of fiber and carbohydrates. The polypeptides in the proteins are not very large. Coriander's 5 major bands were under 97 kilodaltons, while Cuphea's major bands are under 53 kilodaltons. The brassica seed proteins showed 8 to 11 polypeptide bands, with the darkest ones resolving under 31 kilodaltons for Camelina and 41 kilodaltons for Pennycress. Knowledge of soluble proteins is helpful in crafting extraction methods. The soluble protein groups in the four oil seeds were extracted sequentially using water, saline, alcohol, acid, and alkali. Each supernatant was collected and freeze-dried. Its mass and protein contents were recorded. The gluteins make up about half of the protein groups in Cuphea, while globulins, albumins, and acid gluteins are the major fractions in Camelina. In Pennycress, globulins and albumins are dominant. The amino acid contents are a measure of protein nutritional quality. New plant proteins are often compared with soy protein. We use the amino acid score, which is the sum of the essential amino acids minus tyrosine, only as an initial indicator of protein quality. The essential amino acids of rapeseed are listed here for comparison with Pennycress and Camelina. Coriander's essential amino acid contents are like those in soybean. So not surprisingly, their amino acid scores are almost equal. Cuphea's essential amino acid contents are lower, and so its amino acid score is also much less than that of soybean. Camelina's essential amino acid profile gave a score that was greater than Cuphea, but still less than soybean or rapeseed protein. The essential amino acids in pennycress compared well with both soy and rapeseed protein and had an amino acid score that exceeds those of soy or rapeseed protein. We extracted the proteins using the conventional acid precipitation method that was adapted by the soy protein industry. Dilute alkali was added to the ground sample, and the mixture was stirred in a 50-degree C water bath for 90 minutes. After filtering and centrifuging, the protein in the supernatant was precipitated by adding HCl until pH 4.5. The recovered precipitate was redissolved in pH 7 water. After centrifuging, the supernatant was then ultrafiltered and freeze-dried to obtain the protein product. For pennycress, we also did a saline-based extraction given its major protein groups. The freeze-dried protein extracts had high purity. At least 90% proteins were in the pennycress protein extract, which would classify them as protein isolates. The 84% protein in coriander extract and the 80% protein in camelina extract classifies them as protein concentrates. For protein functionality tests, we first determined the solubility at these pH levels, followed by foaming and emulsifying properties, and water holding capacity and heat coagulability. These four properties were tested at pHs where the protein was most soluble, and the details of these tests are described in our published papers. Coriander protein is least soluble at pH 4 and most soluble at pH 5.5 until 10. At this pH range, coriander proteins are much more soluble than soy proteins. At pH 2, the proteins from the dehulled coriander samples were just as soluble as soy proteins. On the other hand, Cuphea seed proteins were poorly soluble from pH 4 to 7 and highly soluble at pH 10. So food use is likely out for Cuphea protein. Meanwhile, the solubility of camelina proteins more closely resembles that of soy protein, with highest solubility at pH 8.5 and pH 2. The saline extracted pennycress seed protein is much more soluble than the acid precipitated protein, showing 80% solubility from pH 7 to 10. The proteins from the press cake were even more soluble, especially the saline extracted press cake isolate, which was highly soluble across all pH values. And this behavior is like that of whey protein. Coriander proteins formed substantial foams. The dehulled coriander proteins had far greater foaming capacity than the whole fruit. This capacity was sustained at pH 2 and pH 10. There's a red dashed line here to indicate the value for soy protein. And as you can see, the foam capacity of coriander protein was still less than that of soy protein at pH 7. So in the next slides, when you see the dashed red lines, that would indicate the soy protein value. We noted the same results for foam stability. Overall, coriander proteins formed stable foams just like soy protein. Cuphea press cake proteins had higher foaming capacity than that of its seed proteins, but the foams collapsed right away. So the foaming properties of Cuphea are actually poor. Pennycress proteins also formed substantial foams, with some samples having foam volumes that were comparable to that of soy protein. The foams were generally stable, with most of the samples showing at least 90% remaining foam after standing for 15 minutes. Coriander proteins were excellent emulsifiers with activity index values that were much greater than the 56 meter square per gram protein recorded for soy at pH 7. These bars are 4 to 6 times greater than the activity value for soy protein. Emulsion stability values like the EAI values also increased with pH. The least amounts were recorded at pH 2. But at pH 7, note that the stability values were greater than that for soy. So coriander protein emulsions are actually more stable than soy protein emulsions. Cuphea's press cake proteins had much greater emulsion activity index values than the seed protein. But it is the seed protein that formed the more stable emulsions. Pennycress seed proteins, especially the saline extracted press cake proteins, showed excellent emulsifying activity and the values increased with pH. You can see here that their EAI values were much greater than that for soy. But it is the acid precipitated pennycress protein isolates that formed the more stable emulsions, with their values almost twice those of the other pennycress protein samples. Cuphea protein's WHC value was unremarkable, but it does match the 3.5 grams of water recorded for soy protein WHC. Pennycress seed and press cake proteins also match the WHC of soy protein, but it is the isolates at pH 10 that gave much higher water holding capacity values. Heat coagulability is expressed as the percent loss of protein solubility. The pennycress protein isolates and the protein in the seed meal were most stable to heating at pH 2. What this means is if you add pennycress protein, say to fruit juice and pasteurize it, there is a low chance of the protein getting denatured and it will retain its functionality. Note that it is the acid precipitated isolate that is very stable across all pH points tested. Camelina protein was also stable to heating, especially at pH 7 and pH 10, which is in contrast to that of pennycress protein. It is the coriander proteins that are most stable at pH 2, 7, and 10, and among the three crops that we evaluated for heat coagulability. So, to summarize, coriander proteins were most soluble at pH 2 and greater than 5.5. They had excellent foaming and emulsifying properties and were stable to heat treatment. They can be used in pressurized foam products or as emulsifier, protein additive, or suspending agent, which is which we actually tested for vanilla grounds and found that coriander proteins were quite effective in keeping the particulates dispersed. Cuphea protein has glutamines as the major protein fraction, and not surprisingly, it is highly soluble in alkaline pH. Its emulsifying properties were comparable to soy protein, and it may be used as emulsifiers in paints or in wood adhesives, just like what we did for soy protein. Wood adhesives have pH around 11. Camelina proteins have globulins, acid glutamines, and albumins as the major protein classes. It is most soluble at pH 2 and 10. Its solubility behavior is like that of soy protein, and it is highly stable to heat treatment. It may be used as a thickener or viscosity agent, as emulsifier, or protein additive. Lastly, the Pennycress seed proteins have albumins and globulins as the major protein classes. They are highly soluble depending on the extraction method that is used. They have excellent emulsifying and foaming properties. They are stable to heat treatment, and their water holding capacity is greater than that of soy protein. We tested them in films, and as you can see, it has a colored but clear film. We tested them in spun fibers and also as a suspending agent for vanilla grounds, just like what we did for coriander proteins. And they were also effective in keeping the particulates dispersed. Other possible uses are as emulsions, whipped product, pressurized foams, or protein additive. And I would like to thank all our colleagues at NCAR who helped us and contributed greatly to the completion of these research projects. Thank you. And thank you very much again for inviting me to this session. And thank you for your kind attention.
Thank you very much to our two main guest lecturers, Dr. Leach and Dr. Hojilla-Evangelista.